Hi! Everyone knows how to find the circuit breaker for a specific outlet. No, we don't do that. You could easily get shocked and electrocuted. And if you ever wake up, you won't have superpowers that allow you to power appliances out of your butt. And even if shorting works, it can cause a big arc and flash that can melt and ruin your outlet. To avoid damage to your outlet, you might decide to cut the end of a power cord, plug that in first, and then short out. No, we don't do that either. I know you're trying to be creative, but stop it! From the time you short an outlet to when the breaker pops open, there is nothing limiting the current but the resistance of the wires. So you may end up popping the building's power, drawing hundreds of amps. Just trust me when I say my sponsor Brilliant is the best place to learn by electrocution-less interaction. Through my link below, you can start your free journey to become an expert in math, science, or computing with the 30-day free trial. More at the end. In any case, if you are trying to pull a MacGyver method, it should be done at safe current levels. A toaster or a hairdryer alone pulls close to the top of the breaker's limit. So two of them together will exceed the outlet breaker current of 15 amps in North American standards, but safely. Just plug them in together and turn them on at their maximum settings and it should pop. It might take a second because the breaker trips slower at currents less than infinity. Finally. Then you open the breaker box to find the popped breaker. What the hell? Nothing is popped here. Oh, I think my power bar breaker has popped. There you go. Oop. Turn it off. You know what? I think there is a better way that can allow us to find all the connected outlets and fuses and even wires in the wall. What if we inject a high frequency like 1 megahertz or something into the outlet, then all the wires will be radiating that signal and we can measure it. Like this, we have a 1 megahertz signal from my function generator we can easily inject into the power line. Alright, we already have the AC power riding on these outlets, so we can't inject a new signal directly into it like that. I guess we could turn off the breaker first, then inject the signal and go measure to find the corresponding breaker. What? Which idiot wrote this script? There is already 60 Hz AC power riding on these wires, and we know we can't sense that. I already made a video making a sensor for it, and there are these live wire sensors. Oh. I left it on and the coin cell batteries are dead already. And this is pretty old. Let's go grab a new technology. So I bought this. Runs on 2 AAA batteries, and unlike this old garbage, it auto shuts down after 4 minutes so your batteries won't die if you accidentally leave it on. You power it on and you sense with it. It senses the live wire right beside it, so you can actually tell between live and neutral wires, which is very good, but my old one did more. Let's power it up. I'm powering it from some AAA batteries. It has a knob that tunes its sensitivity, something the new one doesn't have. So I can set the sensitivity low and tell between the live and neutral wires like the new device. Or set the sensitivity high and actually scan and find the live wire inside the wall. See? I can trace and find the wires inside the wall, something the new device can't do. Maybe I can manually adjust the sensitivity in this one. Let's open it up. Look at this. This blade picks up the electric fields radiated from the live wire like in capacitive coupling. and that voltage goes straight into the Texas Instruments microcontroller to be sensed without any additional amplification. The microcontroller then controls the beeping and LEDs and auto power off. Sometimes it feels like microcontrollers make electronic design easier and lazier. I like an adjustable sensitivity, so I guess I'm stuck with my old sensor. I could use it with AAA batteries. It only needs 2 for 3 volts. But I figured I can use 3 dead batteries. They still have some rotten juice. In any case, all these breakers have the AC voltage on them, so they all beep. I guess you can turn them off one by one to see which breaker is which, or just read the chart provided here. But this is not always available, and you don't want to reset everything at home. So here's the thing, I was watching a Big Clive's video where he was tearing a breaker open, and the breaker had a current sensing coil in it, which gave me big hopes. Quickly crushed by the fact that it was a European style breaker and the North American breakers don't have that. Look at this breaker. I'm measuring around 150 nanohenry only across it, which is similar to a straight piece of wire. But I'm hoping the inductance in this and its contacts in the breaker panel is enough to help. Let me tell you why. The wires from an outlet run into the breaker panel, which also connects to the rest of the house and goes out to the city power transformer, which has a huge inductance. Now if I introduce a signal with high enough frequency at this outlet, it meets with the huge impedance at the city transformer. So for that frequency, city lines look like an open circuit, which means my signal will not be loaded by the 120 volt AC. The two voltages will just add up to each other and coexist on the same lines at home. This is how Ethernet over power line devices can operate. Now I'm also hoping that the breaker on my main signal line also introduces enough impedance to the rest of the house to somewhat block my signal so that the signal is larger on the breaker I'm trying to find compared to other breakers. If I can't find that largest signal, I can tell which breaker is connected to my outlet. To inject my signal into the live wire, we don't directly connect them, but we can pass it through a small high voltage capacitor like 10 nanofarad. If our signal is like 1 megahertz, the capacitor impedance would be around 16 ohms and the signal will be passing through the capacitor easily. But the impedance for the 60 Hz line frequency would be over 260,000 ohms, easily blocked by the capacitor, so it can't hurt my function generator, so we should be able to... Oh, there are these circuit breaker finder devices out there already. Let's buy one. Okay, I bought this two-piece device. This side is an outlet and GFCI tester that apparently also injects a signal into the power line like what I was trying to do. These LEDs show that the outlet wiring is correct, and pressing that button tests the GFCI. If the GFCI is healthy, pressing that button shuts down the outlet. I assume they are doing the same thing I've been always doing, connecting a resistor between live and earth. So you plug this into an outlet that you want to find the circuit breaker for to inject the magic signal into it. And on this side, this thing has a sensor that you can scan the breakers with. It sounds like a metal detector. Oh, there you go. And it finds the right breaker. If I turn it off, the signal goes away too. And if I turn it back on, there you go. It seems like the sensor doesn't sense well anymore after some sensing due to some active gain adjustment, I assume. So you move it away from the signal, press the reset button, and it starts sensing again. So it works, but what is it injecting into the power lines? Thanks to our North American plugs, we can pull it half out, and it is still connected, and probe the live contact. There doesn't seem to be anything. Hey, what is that thing on the peak? It seems like there is a pulse happening on some of the peaks, Every like 7 to 8 peaks, that is around 7 to 10 microseconds wide, which translates into somewhere around 100 to 150 kilohertz. If we probe the neutral line as well, you'll see the signal is there but reversed. The peak of the signal is around 45 volts or 90 volts combined. That's a huge signal. Yeah, and it happens right on the positive peak only. It's guessing time. How did they make this happen? Because we see drop on positive power and rise in negative, it means they are connecting a large load, drawing a ton of momentary current between the lines, and the line voltage drops over wire resistance and inductance. In fact, we should be able to pick up the magnetic fields from such high current pulse using an inductor with a ferrite core like this. Let's see. Oh, look at that. Only the high frequency signal is sensed. I wonder if we put a capacitor across the inductor to create a resonance circuit around 150 kilohertz, we might be able to amplify and stretch the signal. The capacitor is added. Let's see if it can sense any better. Oh, la boom! Let's zoom out a little bit. The pulse on the sensor goes straight so far, much easier to detect. I wonder if they're using the same thing in this. Ha, look, a tiny inductor glued in there across a capacitor here for resonance. Then they amplify the signal through this standard operational amplifier and send the signal to this mystery microcontroller for beeping and stuff. If we probe across the capacitor, hey, there's something. Let me zoom out. There it is. Although it looks like they are resonating at around 10 kilohertz. So back to this thing, to create the pulse of current, I bet they sense the live voltage, and when it reaches the peak, they switch a discharged capacitor across live and neutral for a few microseconds. Capacitor at 0 volts placed across 170 volts draws a ton of current. That seems to also be resonating with the wire inductance. They should have a high value resistance across the capacitor to discharge it again when the switch is off. Let's cut this open to see if our guess is right. That didn't help. Jerry knife. Why don't I accidentally cut myself again? Yeah! Finally, some simple circuit. Even simpler than I thought. Look at this. Well, you can ignore the diodes and LEDs on the top. They indicate the health of the outlet. See that power resistor? When you press this switch, that power resistor falls between live and earth, like I always do, creates an imbalanced current between live and neutral, and triggers the GFCI. And like I thought, these capacitors are the ones that are switched between the power lines to create a huge amount of current with the help of this tiny component as the switch called a SIDAC. I always thought it was a diac. SIDAC is a new name to me. To simplify, when the voltage across this component rises above some fixed threshold, it switches on and in this design places the capacitor between the power lines. And when the voltage across it is too small or the current through it is negative, it turns off. Basically, what I'm saying is that I was right. Kind of. Well, my circuit would do the same thing, just that this SIDAC design seems simpler. One important thing about this measurement method is that we are measuring the magnetic fields created by the pulse of current. So we can only measure where the current is flowing. For example, this power cord is plugged into the same outlet, but there is no current running through it. So we don't measure anything. Well, we learned so much. But don't let that stop you from learning even more at my sponsor, Brilliant.org. It has a 30-day free trial. There is nothing to lose, tons of knowledge to learn, and lots of fun to be had. A great replacement to that stupid addictive game you are playing on your phone or those endless scrolls through TikTok. Your idle time doesn't need to be a waste anymore. You can learn from thousands of interactive lessons in math, data analysis, programming, AI, and more. And they often keep adding new lessons too. You learn anytime suits you best, and just like that, you become an expert in what you need. Brilliant has made learning easy and enjoyable through hands-on interactive lessons. This is the best way to gain problem-solving skills by learning how your adjustments make different results and helps you remember what you learned. I used to be very good at math. I used to be a very good programmer. Most of the knowledge is vaporized from my brain over many years. Brilliant puts me at ease though. Their collection of valuable knowledge is what I can always refer to remember or learn everything I need. So make sure to use my link brilliant.org/electroboom, because on top of the 30-day free trial, my viewers get a lifetime 20% off of Brilliant's annual premium subscription. 10 million people are learning there right now. Be the 10 millionth and first person. And thank you for watching.